This video is going to cover our Principles of Chemistry Lab gas law section. So we start off with three states of matter. We have gas, liquid, and solid. A gas has no definite shape, and its volume is the volume of the container. There's no interactions between the molecules. A liquid has definite volume but no shape, and solid has shape and it has volume. So then we ask ourselves, what is gas pressure and how do we measure it? Let me go over what pressure is. Pressure is the force per unit area exerted against the surface. We use a barometer to measure atmospheric pressure. So how this works is that we have this long glass tube that is that has mercury inside, and then on the top we have this empty vacuum space. There's no gas there, there's nothing there, it's just vacuum. And then we have the glass rod is in the mercury dish. So this dish is open to space. It's open to the air. What happens is the pressure on the dish pushes the mercury up or down, and that's how we measure atmospheric pressure. Pressure is measured in millimeters of mercury, and it's also measured in torr. At sea level, the atmospheric pressure is 760 millimeters of mercury. We use another simpler instrument called a mercury manometer to measure pressure of the gas. So how this is done is that, let me zoom in here so you can see. We have this U-shaped apparatus. In the area A, there's no gas, so it's a vacuum, right? There's no gas, there's nothing there. And in B, we have our gas sample. So what happens is that the mercury travels up into the A area, depending on the pressure of the gas. And when we take the difference between A and B, how far the mercury went up, that is our millimeters of mercury that traveled, so we can determine our pressure. So the more gas we add into B, the more of that mercury is going to go up to A, right? So the pressure would increase because we're pushing these molecules tighter, closer, because our space is limited. So the more we add, the more tighter it's getting in there. Some pressure conversions for you to consider when doing calculations. 1 atmosphere is 760 millimeters of mercury, 760 torr, 101,325 pascals. That's all we use in this class. You don't have to know inches of mercury in bars. So by doing these kinds of experiments, scientists have established different types of relationships between the gas, its volume, its temperature, and pressure. We have multiple relationships that we're going to go over, and you'll have a better understanding of how gas laws take place. Our first law is Boyle's law, and this is a pressure-volume relationship. So Boyle's law states that for a fixed mass of an ideal gas at a constant temperature, the volume of the gas is inversely proportional to the applied pressure. So, example we have here is if the pressure doubles, the volume decreases by 1/2. So we can state this mathematically. we say our pressure 1 times our volume 1 is equal to the pressure 2 times the volume 2. Our by 1 we mean the initial, and by 2 we always mean the final. Boyle's law is seen in breathing. Under normal resting conditions, we breathe about 12 times per minute, each time inhaling and exhaling about 500 milliliters of air. So when we inhale, we breathe in, we lower our diaphragm, and we raise our rib cage, right? That increases the volume of our chest cavity. Therefore, we're increasing in volume, decreases the pressure inside our chest cavity, causing the air to flow into the lungs. And then when we're exhaling, so we breathe out, right, our diaphragm rises and our rib cages are lowered, and this decreases the volume of the chest cavity. Therefore, we get decrease in volume and increases the pressure inside the chest cavity, causing the air to flow out of the lungs. Next, we have the Charles law. Charles law is a temperature-volume relationship. It states that the volume of a fixed mass of an ideal gas at a constant pressure is directly proportional to the temperature, and this is in Kelvin. So when you have a problem containing temperature, make sure you always convert it to kelvins. And how do we do that? To go from degrees Celsius to Kelvin, we have our degrees Celsius plus 273 is equal to Kelvin. So here we have a constant pressure. Our volume and our temperature is changing. And we can write that mathematically, where we have our volume 1 over our temperature 1, which is the initial, is equal to volume 2 and over temperature 2, which are the final volume and temperatures. An example of Charles law is hot air balloon. Because the balloon can stretch, the pressure inside remains constant. And when the air in the balloon is heated, right, we're heating it, we're increasing the volume, the balloon expands, and the air in the balloon, as the air in the balloon expands, it becomes less dense than the surrounding air. That's why we're able to lift up. If you've seen hot air balloons, they have constant fire burning because we're heating it, right? We're increasing the volume. Our third gas law is Guy-Lussac's law, and that is a temperature-pressure relationship. So that states that for a fixed mass of gas at a constant volume, the pressure is directly proportional to the temperature. Again, in Kelvin. Remember, any temperature we have to change from Celsius to Kelvin. So for temperature-pressure relationship, we have constant volume. Volume doesn't change here. We can express this mathematically. Pressure 1 over temperature 1, which is our initial pressure and temperature, is equal to pressure 2 over temperature 2, which is our final. An example of Guy-Lussac's law is autoclave. So steam generated inside an autoclave at 1 atmospheric pressure has a temperature of 100 degrees Celsius. As the steam is heated further, the pressure within the autoclave increases, right? So we have temperature and pressure changing. The valve controls the pressure inside the autoclave. If the pressure exceeds the designated maximum, the valve opens, releasing the steam. At maximum pressure, the temperature may reach 120 to 150 degrees Celsius. all microorganisms in the autoclave are destroyed at such high temperatures. So we can combine these gas laws. All three gas laws that I just went over, we can combine it into this equation of P1V1 over T1 is equal to P2V2 over T2. So we have our starting pressure, starting volume, starting temperature is going to equal to our final pressure, final volume, and final temperature. Whenever we have any gas problems, we use these combined gas laws, and whatever is constant just gets deleted out, and then we can figure out how to work the problem. So I'm going to go over a few examples. Example 1. A gas occupies 3 liters at 2 atmospheric pressure. Calculate its volume when we increase the pressure to 10.15 atmospheric pressure at the same temperature. So, same temperature, right? Therefore, T1 and T2 are constant. We can just take them out of the equation, and we're left with P1 V1 is equal to P2 V2. So, what I did is we take our combined gas law here, right? And our temperatures are constant, so those get canceled out. And we're left with P1 V1 equal to P2 V2. So we're looking for V2 because we know P1, 2 atmospheric, we know P2, 10.15 atmospheric, and we know our initial volume, 3 liters. So we'll get V2 alone, set up the equation, plug in the numbers, and calculate. So V2 calculates to 0.591 liters. So when we increase the gas pressure to 10.15 atmospheric, our volume will be 0.591 liters. Next example. In an autoclave, steam at 100 degrees Celsius is generated at I forgot to mention here. So our example 1, we had P1 V1 equal to P2 V2. I'm going to go back to show you which law that was. P1 V1 is equal to P2 V2 right here. And that is our Boyle's law. So example 2. In an autoclave, steam at 100 degrees Celsius is generated at 1 atmosphere. After the autoclave is closed, the steam is heated at constant volume until the pressure gauge indicates 1.13 atmosphere. What is the final temperature in the autoclave? So we have 100 degrees Celsius, right? We have to convert that into Kelvin, and we get our starting temperature. So if you remember the equation, it was degrees Celsius plus 273, we get the Kelvin. So 100 plus 273, we get 373 Kelvin, our starting temperature. Our starting pressure was 1.00 atmosphere, and we are going up until our pressure reaches 1.13 atmosphere. So the volume obviously is not changing, therefore volume V1 and V2 get canceled out, and we are looking for T2. So in our equation, V1 and V2 are canceled out, and we gotta get T2 alone. So to get T2 alone, we get P2 times T1 over P1. Plug in those numbers, and our second temperature, so our final temperature, will be 421 Kelvin. Right, so our temperature went up from 373 to 421 in Kelvin. Our next example, Actually, before I do that, example 2, remember we had P1 T1 is equal to P2 T2. Which law was that? P1 T1, P2 over T2 is Gay-Lussac's law. Example 3, a gas in a flexible container has a volume of 0.5 liters and a pressure of 1 atmosphere at 393 Kelvin. When the gas is heated to 500 Kelvin, its volume expands to 3 liters. What is the new pressure of the gas in the flexible container? So, what do we have here? So we have volume, pressure, temperature. We have all three. So we'll set up our combined gas law. P1 V1 over T1 is equal to P2 times V2 over T2. In a flexible container has a volume of 0.5 liters. Our starting volume is 0.5 liters, V1. And the pressure,
Here's something I found on the web. According to Jiska.com, its initial volume is 1.75 liters.
That is Alexa talking. Sorry, guys. So our starting pressure is 1 atmosphere, and we have our temperature, starting temperature in Kelvin, 393, so we don't have to convert it. When the gas is heated to 500 Kelvin, so that's our ending final temperature, 500 Kelvin, the volume expands to 3 liters. That's our final volume. So we're going from half a liter to 3 liters. And we're going from 393 Kelvin to 500 Kelvin. So what are we missing? We're missing our final pressure. And that's what we need to calculate. So we have to get P2 alone. So we'll rearrange our equation. And we get P2 is equal to P1 times V1 times T2 over T1 times V2. We'll plug in all the numbers. Liters cancel out. Kelvin cancels out. We're left with atmosphere. Pressure is in atmosphere. So our P2 is 0.21 atmospheric. Next we have standard temperature and pressure. To select one temperature and one pressure as standard, chemists have chosen 1 atmosphere as the standard pressure and 0 Celsius or 273 Kelvin as the standard temperature. These conditions are called standard temperature and pressure, also known as STP. So anytime a problem tells you it's at standard temperature, standard pressure, know that for standard temperature we plug in 1 atmosphere. For temperature we plug in 273 Kelvin, and for pressure it's 1 atmosphere. All gases at standard temperature and pressure or at any other combination of temperature and pressure contain the same number of molecules in any given volume. But how many molecules is that? What volume of gas at STP contains 1 mole of molecule? This quantity has been measured experimentally and found to be 22.4 liters. Thus, 1 mole of any gas at standard temperature and pressure occupies a volume of 22.4 liters. Avogadro's law allows us to write a gas law that is valid not only for any pressure, volume, and temperature, but also for any quantity of gas. And this law is called the ideal gas law. The ideal gas law is PV is equal to nRT. P is our pressure in atmospheric, V is our volume in liters, N is the amount of gas in moles, R is the constant, it's a constant for all gas, it's called the ideal gas constant, and T is the temperature of the gas in Kelvin. The value of R can be found by using the fact that 1 mole of any gas at standard temperature and pressure occupies a volume of 22.4 liters. So, if you remember, standard temperature and pressure, we have 1 atmosphere and we have 273 kelvins for 1 mole of gas. Our volume is 22.4 liters, so when we plug that in and we get our R alone, we rearrange our equation, we plug in all the values, we get that the R is equal to 0.0821 liters times atmospheric over moles times Kelvin. This is a constant, so R will always be 0.0821. Our next example says if there is 5 grams of carbon dioxide gas in a 10-liter cylinder at 25 degrees Celsius, what is the gas pressure within the cylinder? So, we are given the quantity of carbon dioxide in grams, right? 5 grams. But to use the ideal gas law, we must express the quantity in moles. So first we're going to convert grams of carbon dioxide to moles of carbon dioxide. How do we do that? So 1 mole of carbon dioxide, carbon is 12, oxygen is 16. We have 2 oxygens, so we'll multiply 16 by 2, and we get our 44 grams of carbon dioxide is 1 mole of carbon dioxide. Then we convert the grams to moles. Because we are using 5 grams, so we multiply 5 grams of carbon dioxide by 1 mole of carbon dioxide over 44 grams. Because we want to get our moles, so our final answer needs to be in moles. Remember, the grams has to be canceling out. That's why we put 1 mole over 44 grams of carbon dioxide. When you cancel out the grams, you're left with mole, and that gives us 0.11 moles of carbon dioxide. Then we use the equation I went over, right? Our ideal gas law equation is PV is equal to nRT, right? Remember, R is the constant I went over, 0.0821. So now we are looking for pressure. So we got to get pressure alone on one side of the equation. So P is equal to nRT over V. We plug in all the values. Pressure is equal to our number of moles is 0.11 moles of carbon dioxide times our R is 0.0821, and the units are liters times atmospheric over moles times Kelvin. We multiply that by the temperature, which is 298 Kelvin, right? 25 degrees Celsius. 25 degrees Celsius plus 273. That gives us 298 Kelvin. All math for temperature is in Kelvin. And we divide that by our 10-liter cylinder. And we get our pressure is equal to 0.27 atmospheres. And that's it for today, guys. Just remember, all the temperature is in Kelvin, and our R value is always a constant, 0.0821, and our combined gas law, P1 V1 over T1 is equal to P2 V2 over T2. Alright guys, that's it for today.